They had no iron tools, so how are these cuts laser precise? The blocks were already cut before Rome was born. That's the part they don't put in the textbook caption. They show you the photograph, they label the civilization, they give you the date, and they move on. But if you stop and look at the actual stone, if you get close enough to run your hand along the edge, you find something that doesn't fit the timeline at all. We're talking about right angles so sharp they could slice paper. Grooves exactly 6 millimeters wide, running in perfectly straight lines for the entire length of a block, with equidistant drilled holes spaced along them like perforations on a factory-made part. Joints between multi-ton stones so tight that a razor blade cannot be inserted between them. And all of this, every last cut, every last hole, every last surface produced by people who, according to the official version, had no iron tools, no steel, no machinery, just stone, copper, and their hands. If you've been following this channel for a while, you already know the pattern. The data keeps piling up, and the explanations keep falling short. Hit that subscribe button, because this is the kind of territory we go back to again and again, and it never gets old. Now, let's talk about what the official version actually says, because it needs to be said out loud before we dismantle it. The standard explanation goes something like this. Ancient builders used stone hammers, wooden mallets, and copper chisels to shape even the hardest stone, granite, diorite, andesite. They used abrasive sand as a cutting medium. They rubbed, pounded, and ground their way through material that ranks between 6 and 7 on the Mohs hardness scale. Copper, for reference, sits at about a 3. You are, in the official version, cutting a 7 with a 3, and producing results that look like they came off a CNC machine. That's not fringe speculation. Pink granite, sourced from Aswan, is among the hardest natural stones, registering around 6 to 7 on the Mohs scale harder than copper, which rates at only about 3. Those numbers matter. Hardness in geology isn't a loose estimate. It's a physical property. A material ranked lower on the Mohs scale cannot, under normal conditions, cut a material ranked higher without an abrasive intermediary doing the real work. So when the textbook says copper chisel meets granite, the copper chisel is not doing the cutting. The question is, what is? The answer mainstream archaeology gives is quartz sand. You press a copper tube into granite, you pour wet sand into the gap, and the sand, which is harder than granite, does the grinding. Several replication studies, particularly those by Denny Stocks in the 1990s, demonstrated that copper tubes with sand slurry could indeed cut granite when operated over long periods. However, Stocks himself acknowledged that producing deep, rapid cuts required extensive time and labor. Thousands of rotations per hole. Thousands of rotations per hole. And some of these sites have hundreds of holes, identical holes, equidistant, uniform depth, uniform diameter. That answer starts to bend under its own weight. And now here's where it breaks. In 1880, a British engineer and archaeologist named Flinders Petrie sailed to Egypt. The first precise measurements of the pyramid were made by Egyptologist Flinders Petrie in 1882, published as The Pyramids and Temples of Giza. Petrie was not a mystic. He was not a conspiracy theorist. He was, by almost any measure, the founder of modern scientific archaeology in Egypt, the man who brought tape measures and precision instruments to a field that had previously been running on guesswork and romanticism. He wanted to measure things exactly. And what he found when he measured exactly is still sitting in a museum in London, quietly defying explanation. Many of the casing stones and inner chamber blocks of the Great Pyramid fit together with high precision, with joints, on average, only 0.5 millimeters wide, half a millimeter. Let that sit for a moment. We are talking about blocks of limestone weighing multiple tons apiece, some as large as a car, some larger than a truck, fitted together with a tolerance that a watchmaker would be proud of. The joint between them, half a millimeter, on average, across the entire outer casing. Petrie didn't find this surprising in a sensational way. He was an engineer. He found it surprising the way an engineer finds something surprising with a quiet, measured unease. Because he knew what it takes to produce that result. He had spent years working in precision manufacturing, and what he was looking at on the outside of a 4,500-year-old pyramid was a level of fit that would be considered excellent by the standards of the workshop he had left behind. But the joints were only the beginning. While working at Giza, Petrie also collected a series of granite drill cores, pieces of stone left behind inside boreholes, the byproduct of the drilling process. These cores were broken off during ancient construction and left in the rubble. Petrie brought them back to London. They sat in the museum. And decades later, an engineer named Chris Dunn got close enough to examine them properly. The most fascinating feature of the granite core Petrie describes is the spiral groove around the core, indicating a feed rate of 0.1 inch per revolution of the drill, 500 times greater than modern diamond drills. Read that again. 500 times greater. Not faster, the distinction matters. The ancient drill was not spinning faster than a modern diamond drill. Modern diamond drills penetrate at only 0.0002 inch per revolution. The ancient core shows 0.1 inch per revolution, meaning for every single rotation of the drill, it was biting into the granite 50 times deeper than the most advanced diamond-tipped equipment we have today. Petrie himself noted that the spiral groove could only be explained, in his words, by the use of fixed cutting points, jewel points embedded in the drill head, not sand, not abrasive slurry. Fixed points. Alternative researchers maintain that the precision, depth, and spiral uniformity in the granite core cannot be explained by simple hand tools. And when replication experiments have been run, even recent ones, laboratory experiments attempting to replicate the results using copper tube drills and abrasives have achieved only partial success. While grooves can be formed, the efficiency, depth, and spiral consistency seen in Petrie's core remain unmatched by simple abrasive methods. This is not fringe journalism. This is materials science. This is the data. And here's where it gets uncomfortable. Egypt is not alone. 12,800 feet above sea level, on the Bolivian Altiplano near the shores of Lake Titicaca, there is a site called Puma Punku. It is part of the larger Tiwanaku complex, and it is, in the measured, careful language of researchers who have actually stood there with instruments, one of the most technically inexplicable places on Earth. The red sandstone and andesite stones were cut in such a precise way that they fit perfectly into and lock with each other without using mortar. The technical finesse and precision displayed in these stone blocks is astounding. Not even a razor blade can slide between the rocks. No razor blade, no mortar, just stone, fitting stone, perfectly, at nearly 13,000 feet elevation, in a location where the air is thin enough that heavy physical labor becomes a medical risk. At Bolivia's Puma Punku, megalithic stones display machine-like precision with perfectly straight lines, right angles, and smooth surfaces. The Tiwanaku civilization lacked metal tools and the wheel, yet created cuts accurate to within fractions of millimeters. Now look at the specific cuts, because this is where Puma Punku stops being a curiosity and starts being a problem. There is a block that gets the most attention, a perfect groove with identically spaced, precision-cut 6mm holes drilled along the cut. 6mm, perfectly round, perfectly equidistant. Drilled into andesite, one of the hardest stones found in the Andes. The modular blocks of the site, also called H-blocks, show a high degree of precision both in the notching of the right angles and in the measurements related to each block. Now, here's what the H-blocks actually tell us when you examine them closely. From measurements, researchers have discerned that no two H-blocks are of the exact same size, and thus each one had to have been made individually. This throws out the idea that they were mass-produced using a mold of some kind. Think about what that means. Every single one was custom-made, to its own unique dimensions, but to tolerances of fractions of a millimeter, one-off production, at sub-millimeter precision, in andesite, with no iron tools. Modern engineers have compared the precision to what we achieve today with laser technology or CNC machining, yet Puma Punku predates such tools by over 1,000 years. Coincidence? Possibly. But a coincidence that appears not once, not twice, but in stone after stone after stone, across thousands of miles of separation, on different continents. And here's another layer, the metal clamps. At Puma Punku, many of the stone blocks were held together with metal clamps, H-shaped staples poured directly into recesses carved into the tops of the blocks. This is an old technique, used in various forms across the ancient world. But at Puma Punku, the clamps are made from an alloy, and that alloy contains nickel. There is no source of nickel anywhere in Bolivia. Recent scans have revealed that metal was poured into these indentations, which means the builders had portable smelters. Portable smelters in the middle of the Bolivian highlands, producing a nickel alloy for a people with no iron, no wheel, and no writing system. If that alone is hard to explain now, it gets really interesting. Cross the Atlantic, move north along the eastern Mediterranean coast into what is now Lebanon. You arrive at Baalbek, a site that was built over by the Romans, who constructed one of the largest temple complexes in the ancient world on top of it. The Roman work is extraordinary by its own standards. But beneath the Roman work, in the foundations, there is something that the Romans themselves appear to have found useful as a base, because they built on top of it rather than replacing it. The foundation stones at Baalbek include individual limestone blocks of staggering size. One still sits in the nearby quarry, unfinished, never moved. It is known as the Stone of the Pregnant Woman, and for centuries it held the record as the largest known cut stone in human history. It weighs approximately 1,000 tons. Newer excavations nearby have since uncovered a second stone at roughly 1,650 tons, making it the heaviest known quarried stone on Earth. In Lebanon's Bekaa Valley, the Roman temple complex of Baalbek stands testament to the grandeur of the Roman Empire. Yet beneath the impressive Roman ruins lie foundations of even greater mystery. Massive megalithic blocks that predate Roman construction by centuries, possibly millennia. The Romans, who could move stone well enough to build the Pantheon and the Colosseum the Romans built on top of the Baalbek foundation, they did not claim it, they did not recut it, they used it. As if they understood that whatever process created, it was beyond their own capability to reproduce. Now, back to Egypt. One more case. In the Serapeum at Saqqara, there are granite boxes, not decorative containers, massive sarcophagi carved from solid Aswan granite, each one weighing in the range of 70 tons, housed in underground chambers carved directly from the living rock. The manufacturers of these boxes not only created inside surfaces that were flat when measured vertically and horizontally, they also made sure that the surfaces they were creating were square and parallel to each other, with one surface, the top, having sides that are 5 feet and 10 feet apart. Without such parallelism and squareness, the squareness noted on both sides would not exist. An engineer who spent 40 years in precision manufacturing looked at those boxes and wrote, "While it may be argued that modern man cannot impose a modern perspective on artifacts that are thousands of years old, an appreciation of the level of precision found in these artifacts is lacking in archaeological literature and is only revealed by an understanding of what it takes to produce this kind of work. This accomplishment in prehistory deserves more recognition." Deserves more recognition. That's the polite way of saying the textbooks are not asking the right question. We're not at the core yet, but we're close. Let's lay the data points side by side. 1. The Great Pyramid's casing stones, measured by Petrie in 1880 and confirmed since, show joint tolerances of 0.5 millimeter across an area the size of several football fields using blocks of multi-ton limestone, fitted without modern surveying equipment, in the year 2560 BC, give or take. 2. The granite drill cores from Giza show a feed rate into hard granite that is 500 times deeper per revolution than the best diamond-tipped industrial drilling equipment available today. The spiral is continuous, the groove is uniform. Copper and sand do not produce this result in any replication experiment that has been run. 3. At Pumapunku, Bolivia, 12,800 feet above sea level, a civilization with no iron, no wheel, and no writing system produced andesite blocks with fractions of a millimeter precision, custom cut to individual specifications, fitted without mortar, joined with metal clamps made from a nickel alloy that does not occur naturally anywhere in the region, and the process by which any of this was done remains, in the careful language of the peer-reviewed archaeological literature, largely unexplained. 4. At Saqqara, 70-ton granite boxes were produced with interior surfaces so flat, so parallel, so square to one another that a 40-year veteran of precision manufacturing calls the achievement extraordinary and notes that its implications are absent from the archaeological conversation. 4 data points, 4 separate continents, 4 civilizations with no known contact, 1 pattern. Now, here's the inversion that changes everything. We've been asking the wrong question. The question we've been asking is, how did primitive people produce these results? And because the question contains the word primitive, every answer it generates has to be a story about improvisation, about clever workarounds that happen to produce results better than anything we can replicate today. That's a strange kind of clever. That's not improvisation, that's capability. The better question, the one the data actually points toward, is not how did they work around their limitations. It's whether the limitations we've assigned to them are real. Because if a civilization can drill into granite at 500 times the feed rate of modern diamond equipment, the limitation is not theirs. The gap is in our understanding of what they had. Some researchers argue this points to a lost technological tradition knowledge that existed before the civilizations we recognize passed forward in fragmented form to the builders we've cataloged. Others argue the precision itself is overstated, that we are projecting modern manufacturing standards onto ancient craftsmanship and finding coincidences where context explains the data. Both arguments are worth hearing. Both are serious. But here's what's not an argument. The 0.5 millimeter joint is real. The drill core is in the Petrie Museum. You can go look at it. The 6 mm grooves at Pumapunku are there in the stone, carved into andesite, equidistant, uniform, waiting for an explanation that the official version has not yet provided. There are many stone artifacts from the ancient world made from the hardest stone on the planet, granite and diorite, which have been cut and shaped with such quality, precision, and accuracy that the standard explanations of their manufacture are simply inadequate. That's not a conspiracy channel saying that. That's the considered position of researchers who have spent careers in the field. What the official version tells us is that human ingenuity is sufficient to explain every anomaly if we are patient enough and creative enough with the method. And maybe it is. Maybe we will eventually reconstruct, step by step, a plausible sequence of operations that produces a 500 times feed rate on granite using materials available in 2500 BC. But we haven't done it yet. And until we do, the stone keeps asking the question. The cuts are there, the grooves are there, the tolerances are there. And the tools that could have made them according to what we know, according to what the ground has given us, are not, that's not a theory, that's the record. What stands above the ground is only half the story. The chambers beneath Saqqara, the tunnels under the Giza plateau, the underground surveys that have been quietly changing what we thought we knew about the age of these structures, that's where this channel is going next. Because when you move the question underground, the timeline starts to look very different, and the official version gets a lot quieter.